Welcome back to the class on a power semiconductor drives. In this lecture, we are going to discuss about the slip torque characteristics of a three-phase induction motor. So first, find the what is the relation between the torque development induction motor and a slip of the induction motor. To derive that expression, we are starting with this is the per phase equivalent circuit of a three-phase induction motor. This is the stator resistance. This is the stator leakage reactance. This is the rotor leakage reactance with respect to the stator. This is the rotor resistance with respect to the stator. This is the magnetizing reactance. We neglected the core losses. In case of induction motor, we can't neglect the magnetization current because the magnetization current of induction motor is more when compared to the transformer. So this is the one of the approximate equivalent circuit of a induction motor. RR dash by S. It is consisting a rotor resistance and the resistance which is equivalent to the mechanical power development induction motor. This is the input voltage. Now the important term in a three-phase induction motor is the slip of the induction. It is defined as ratio between the difference in a synchronous speed of a motor to the actual speed of a motor to the synchronous speed. The slip of the induction motor equal to omega ms minus omega m by omega ms. Nothing but this is synchronous speed, this is the actual speed of a motor, where omega is equal to nothing but a synchronous speed in a radians per second equal to 4 pi f by. If you know the synchronous speed in a radians per second, the rotor speed equal to synchronous speed in a radians per second into 1 minus s. From the equivalent circuit, the rotor current referred to the stator is equal to, if we neglect the magnetization current, so this rotor current equal to stator current, that is equal to this voltage divided by the impedance of this circuit. Here the two resistors are there, Rs and Rr dash by S, that we combine here, plus J, XS, nothing but a stator reactance and rotor reactance with respect to the stator, that we combine here. J is nothing but an operator. Now we are finding the power transfer to the rotor, nothing but a air gap power also. That is equal to 3 times the IR square into Rs by S. This is nothing but a three-phase rotor copper loss divided by the slip of the induction motor gives the air gap power or power input to the rotor. Now the rotor copper loss equal to this numerator 3 IR square into RR dash. The actual mechanical power developed in an induction motor is equal to this rotor input minus this rotor copper loss, that is equal to the PM equal to air gap power minus copper loss. If you substitute these values in this equation, if you simplify, we are getting the 3 IR dash square into RR dash into 1 minus S by S. Now already we know that the torque equal to this power divided by the angular speed of a rotor. This we can write it as a omega S into 1 minus S, substitute here. In place of PM, you substitute this value, then finally you are getting the developed torque equal to 3 into IR dash square into RR dash. This is the synchronous speed of a motor into slip. Already we know the value for this rotor current. This is the vector form of the rotor current. Now in this place, you substitute this one, we are getting the developed torque equal to 3 by omega ms into V square into RR dash by S divided by Rs plus RR dash whole square plus XS plus XR dash whole square. This is the expression for the torque developed in an induction motor, which gives the relation between the torque and slip of the induction motor. Now suppose if you want to find out the maximum torque developed in induction motor, because the torque developed in induction motor is a function of a slip, so we have to differentiate this equation with respect to the slip and equate to 0. We are getting the condition to get the maximum torque developed in a induction motor. The slip corresponding to the maximum torque that we have taken as a Sm equal to plus or minus Rr dash by Rs square plus Xx plus Xr dash whole square. This is the slip corresponding to the maximum torque. If you substitute this value in a torque equation, in this equation in place of slip, if you substitute this one, we are getting the maximum torque developed in a induction motor. We are getting this is the expression for the maximum torque developed in induction motor, that is a 3 by 2 omega ms into V square by Rs plus or minus square root of Rs square plus Xs plus Xr dash whole square. Now we are going to draw the how the torque developed in induction motor as the slip is increases. Already we know that the slip of the induction motor we can change from 0 to 1. If slip is 0, nothing but the speed of a motor n equal to ns. Nothing but omega m equal to omega m. If the speed of the motor is decreases from the synchronous speed, then the slip will be increases. For a low value of the slip, see in this equation, this quantity will be higher when compared to the denominator remaining term. So we can write it as a torque development induction motor that is equal to 3 by omega ms into v square rr dash by s divided by rr dash by s whole square. Scale gets cancelled. So finally we can say that the torque is directly proportional to the slip up to the low value of the. Suppose the slip value is more. When the slip value is more, this value becomes a very, very low. So we are neglecting this quantity. So the torque development induction motor, the T equal to 3 by omega ms into v square rr dash by s divided by rs k plus xs plus xr dash whole square. This whole thing is a constant. So the torque development induction motor is inversely proportional to the slip, for the slip value is higher. So from this we can easily draw the characteristics of a three-phase induction motor. On the x-axis we have taken the torque, on the y-axis we have taken the slip. This is the slip corresponding to the 0. Nothing but the motor will be running at a synchronous speed. For low value of the slip, up to this value, we are assuming that the slip value will be lower. Up to this value, the torque will be increases in this manner. This is nothing but a slip corresponding to the maximum torque. Further increasing the torque, it is inversely proportional. The slip value is more, the torque development induction motor will be inversely proportional to the slip. So it will represent the rectangular hyperbola. This value is nothing but a maximum torque development induction motor. When s equal to 1, nothing but the speed of induction motor is 0. This is nothing but a starting torque. This region, this is the stable region, whereas this is a unstable region. So why you are calling this region as a stable region means, as the slip is increases, the torque development induction motor also will be increases. But here in this region, as the slip is increases, the developed torque in the motor will be decreases. So that's why you always operate the induction motor only in the stable region. We never operate the induction motor in the unstable. These are the slip torque characteristics of a three-phase induction motor. Thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am always available to answer all your